Hello, let's start off with a sample diploma board problem from the half-life stuff. So cobalt-60 is a common radiation source used to treat cancer. The half-life of cobalt-60 is 5.2 years. Okay. A cobalt-60 nucleus decays by emitting beta negative particle and gamma photon. The percentage of cobalt-60 remaining after 15.6 years. Well, we can figure out our half-lives. And our time is 15.6 years, and 5.2 years is our half-life, so that's going to be 3. Right, so you can see it's in terms of percentages. So at 0, you're going to have 100%. At 1, you're going to have 50%. At 2, you're going to have 25%. And at 3, you'll have 12.5%. So that's our answer. 12.5%. Okay, the activity of the sample after 3 half-lives have elapsed. Okay, well, let's take a look. So we start off at, looks like we start off at 4,200. So after the first half-life, we'll have 2,100. Which is here. Oops, can't go too slow. Oh. I guess we don't have to do that. Sorry, I was trying to figure out the time of the half-life, but we can just go 2. We're going to have 1,050, and then 3, we're going to have 525. B. Yeah, that's it. You just had to look at where you started at. That was nice and easy. Thorium-235 has a half-life of 241 days. The percentage of thorium remaining after 18 days. Okay, so 18 days. Half-life is 24.1 days. So we can calculate how many N's. And this one we're not going to get a nice number. But I'm just opening my calculator so we can see that number. So we can go 18 divided by 24.1. And we get, 0.0746. So we can use our n equals n naught 1/2 to the little n formula for this. So again, it's in percentage. So we start off with 100%. And then we just go 1/2 to the, oops, I don't think there's a 0 here, 0.746. And I'll use my full number in my calculator. So I just have to go 0.5 to this, and then multiply that by 100%, and there's going to be 59% remaining. Right. You could eliminate these 2 answers too, because not even 1 full half-life has occurred, so it's not going to have less than 50%. So C is the correct answer. Okay, let's do our last lesson in this course, which is particle physics. So curriculum stuff, explain how the analysis of particle tracks contributed to the discovery and identification of the characteristic of subatomic particles. Explain qualities, qualitatively in terms of strong nuclear force, why high energy particle accelerators are required. And use hand rules, bringing up hand rules from our second unit to determine the nature of charge on a particle. So make sure you remember those hand rules. Describe the modern model of the proton and neutron being composed of quarks. So quarks is a new term that we'll talk about in this lesson. Compare, contrast up quark, down quark, the electron neutrino, and their antiparticles in terms of charge and energy. And describe beta positive, beta negative decay using first generation elementary fermions. So we'll talk about what these words mean right here. Okay, let's get started. So, artificial transmutation. So Marie and Pierre Curie observed as early as 1899 that radioactive uranium made substances around it become radioactive as well. So if you put something by something that's radioactive, it becomes radioactive. So substances that weren't normally radioactive can be made radioactive by bombardment with high energy particles, such as those emitted from radioactive decay. So when you stuck the uranium by a non-radioactive substance, right, it was being bombarded with protons, neutrons, electrons, alpha particles, gamma rays, right? And in this process of artificial transmutation, new radioactive isotopes are formed that may not exist in nature. So number 92, which is uranium, is the heaviest naturally occurring element, but by bombarding it with high energy particles, you can make 93, 94, 95, you can make elements that are not naturally occurring. So in 1919, Rutherford was the first one to artificially transmute nitrogen-14 by bombarding it with an alpha particle. He found a new isotope, oxygen-17, which doesn't exist in nature. Right? So he took this nitrogen, bombarded it with an alpha particle. Top, our nucleons have to be 18, so it makes oxygen-17 and a hydrogen ion, or hydrogen molecule, and then 9 on the bottom, 8 and 1 on the bottom, like that. So law of conservation of nucleons, law of conservation of charge still applies with this. So nowadays, particle accelerators are used to produce high energy particles needed to cause nuclear reactions or transmutations. So there's two types of accelerators. There's linear accelerators, which go in a straight line, and synchrotrons, which travel in a circle. So both consist of long underground buried tunnels. The linear accelerator, example of a famous one is in Stanford, is 3.3 kilometers long. And at the end of those tubes, those long hollow tubes, the electron or proton may have millions of electron volts of energy. So this is a Stanford Accelerator. Here it is right here. You can see the highway goes over top of it. So that's 3.3 kilometers that they shoot subatomic particles down. A synchrotron operates the same way, only it uses a magnetic field to deflect the particles in a circular path. We know that magnetic fields cause charged particles to deflect. And as the particles race around the circle, each loop adds additional energy. So they can go faster and faster and faster each loop. Famous one is Fermi National Accelerator Laboratory in Chicago. It's got a 2 kilometer diameter. Here it is. Right, so you can see from the top view that this is it. This is like a little starter track to get it some speed, and then it goes faster, and then it goes around this one. So one of the most famous ones is in Geneva, Switzerland, CERN. It has linear and circular accelerators, and the largest accelerator is the LEP, Large Electron Positron Collider, which is 27 kilometers around, which is in circumference. So you can see this one here. It's absolutely huge. Right? It's got these littler ones here. It's got a bunch of different tracks. Here's a different picture of it. So it's got all these different tracks, right? It can start here, move here, go here, and then go into the bigger one like that. So, yeah. So why use particle accelerators, you ask? It seems in order to probe smaller and smaller matter, you need larger and larger machines. So when we were first talking about the photoelectric effect, 13.6 electron volts is needed to ionize the hydrogen atom. If you have a few hundred electron volts, you can study the outer shell of electrons. To study the nucleus, when Rutherford did his gold foil experiment, he used 10 times 10 to the 6, so 10 mega electron volts of energy. Right? And then to study the inside of the nucleus, you need enough energy to overcome the strong nuclear force. So the strong nuclear force has a ton of energy, so you need to overcome that. So you need lots and lots of energy. So the first experiments with low energy accelerators were able to split nuclei into lighter elements. With higher energy particles, physicists can make heavier particles if they have a minimum of several giga-electron volts. So to make new particles, you need a lot of energy, and you need these huge accelerators to get that energy. So you need to know about bubble chambers. So a bubble chamber uses liquid hydrogen at almost boiling point. So boiling point for liquid hydrogen is going to be really, really cold. The tiny bubbles of hydrogen condense around charged particles. It's kind of like when it's cooler out and the jet moves through the sky, it leaves that vapor trail behind. That's similar to what's happening here. So if you send a subatomic particle through this liquid hydrogen, it's going to leave a little bit of a vapor trail. The charged particles are put through a magnetic field where they move in circular paths, and you can get things like radius, and you can figure out their mass and their charge depending on their spin. So the radius of the particle can be analyzed to determine momentum and charge of that particle. So you and your partner get these results from a bubble chamber. So we sent a bunch of subatomic particles through a bubble chamber. This is what we see. Your partner identified this as an electron. So we can identify the other tracks. Okay? There's a really easy one to identify. That's C. It has the exact same radius as it's swirling around, right? And it's spinning the exact same way. So C is an electron. What would this be, though? Right? We know, according to our hand rule, that we can figure out the direction of our magnetic field. Right? If you want it to spin in a circle like that, an electron is negative. So grab your left hand, right? And then it always goes from bigger to smaller. So this is the direction that our electron is starting out. So put your thumb in that direction, and we want our palm to sort of push it into that circle. And if you're doing that correctly, you can see that our magnetic field is out of the page. So our magnetic field in this bubble chamber, we'd represent with a dot, is out of the page in this situation, right? So you've noticed that the radius is the same, and the radius has to do with the mass because Fc equals Fm, mv squared over r equals qvb. We can eliminate one of our velocities and move our r up top and our qb down below, and we get that mv over qb is equal to r. Right? So if we assume they have relatively the same speed, same charge, it's the same magnetic field, same mass, right? The mass, if the radius is the same, the mass is going to be the same. The charge is the same. So something with an electron that has the same mass but opposite charge would be a positron. So this is a positron. And then D here, you can see it has a much bigger radius, right? This is the circular path of it. So an electron has the elementary charge, right? And to get a bigger radius, we would actually need a smaller charge, which isn't possible. So it can't be with the charge. It's the same magnetic field in there, right? It could be moving faster, but more likely if with this big radius, what's happening is if we have a bigger mass, we have a bigger radius. Right? And it looks like everything is sort of moving to the right. So it's moving this way. So if we want to figure out something, maybe this is a proton, but if you use your hand rule, right? If it's a proton, you should use your right hand. Put your fingers out of the page and put your thumb in the direction that it's moving. You can see that your palm is facing down. So if it was a proton, it would actually move in a circle like that. So this is some sort of negative particle that's bigger than an electron. Well, what is it, right? And that's what they found. They found weird things that they weren't expecting. So we know it's negative. We know it has a big mass. Maybe an alpha particle, right? It could be an alpha particle for sure. Wait, no, that is a positive charge. It can't be an alpha particle, right? So we don't actually know anything right now that's negative and has a bigger mass than an electron. Yeah, so weird stuff. So in 1937, Carl Anderson and Seth Niedermeyer used a cloud chamber to discover muons. Ooh, these are new particles we've never heard before. So muons are a lot like an electron, but they have a mass that's 207 times greater, right? So that would make sense. That's why it has that bigger radius, because it has a bigger mass. And we know that it's negative because it's flowing to the right. So yeah, that would make sense what's going on in this one. So it must be a muon. So muons are a lot like electrons. They have a mass that are 207 times greater. Later they found pions, which were discovered using a new technology where tracks are recorded on photographic plates. So it's a similar way, right? And then later, when they were eating their Caesar salad, they found croutons. Oh, I ruined the joke. So there's muons, pions, croutons. Just kidding. Bad joke. Whew. So they found over 300 subatomic particles using accelerators and detectors, and most of these particles were very unstable and they had lifetimes of less than a microsecond, and that makes sense why we've never seen them before. So now we have these pions, these muons, they're these new particles. We need to organize, classify things. How do they relate to electrons? How do they relate to protons? So what they came up with is they broke them into two families. So there are leptons, which do not interact using strong nuclear force, and hadrons, which interact using strong nuclear force. So these would be things that are in the nucleus, and these are things that are not in the nucleus, right? So if you think about what we know now, well, what's in the nucleus? Well, protons and neutrons are hadrons because they interact using the strong nuclear force, and they are made of quarks, which we'll talk about in a little bit. Electrons are leptons because they do not interact using the strong nuclear force, and if you're a lepton, you are not made of quarks. Okay, so those are two nice little classifications. So if you see those words, that's what they mean. So hadrons can be divided up into different categories, so they can be subdivided again. So baryons are much heavier than mesons, right? So we have these subatomic particles. So we have leptons, which include electrons and muons, right? So those are both leptons. And then we have our hadrons, which are things that are, might be found in the nucleus, and they divide them into mesons and baryons, right? So baryons are heavy, and these ones are light. Right, so a pion is a light hadron, and then protons and neutrons are heavy versions of that. So it looks like these are a lot lighter. Okay, and then we can subdivide it again. So one more subdivision is categorized by a particle spin. So the momentum of their spin can either be a half integer of Planck's constant divided by 2 pi, and that's a fermion. And then you can also be an integer, so 0, 1, 2, or 3 of Planck's constant divided by 2 pi. That's a boson, right? So leptons are fermions based on their spin. Baryons are fermions based on their spin. And then bosons are mesons based on their spin. Okay, do you need to memorize this? No, you do not. You don't need to memorize any of this. Don't worry about it. You can see it's not in the program of studies. But sometimes you might see these words. So I just wanted to go through this and explain what these words mean, because you might be doing a test and be like, baryon, what is that? But it should explain what it is in the text box. Don't worry if you hear the word baryon. Okay? Don't study this. You don't need this. So what they found is that there's different ways to classify things. Baryons, leptons, mesons, all very confusing, and they call it the subatomic zoo because there's, before today we had electrons, protons, neutrons, and neutrinos, and positrons we talked about before, but now there's neutrino, neutretto, electron, muon, proton, neutron, lambda, sigma, plus, sigma, 0, sigma, minus, pi, xi, z, g, chi, 0, minus, photon, kaon, pion. Oh man, so much stuff to sort out. So yeah, it's like a zoo of animals. There's all these subatomic particles. There's tons of them everywhere. So yeah, subatomic zoo. So in 1963, Americans Gell-Mann and Zweig said that hadrons are composed of smaller particles called quarks. Right. So these hadrons are those neutrons and protons. So they're made up of quarks, so there's something smaller, there's something more quantum than a proton. Okay, so all hadrons could be made from 3 simpler, smaller particles, and they're antiparticles. So these 3 particles are called up quark, down quark, and strange quark. And all these quarks are no longer a charge of 1. They have these fractional charges of plus minus 1/3 or plus minus 2/3. Why? No one knows. So quarks can be broken up into 3 generations. So our first generation are normal matter. And our second and third generation make up short-lived particles that decay into first-generation particles, right? So this is what we need to know, these first generations. So an up quark is 2/3, positive 2/3, a down quark is minus 1/3. And you have these on your data book, I'll show you where. Okay, second generation ones, so their name is also called their flavor, which is kind of like a good, you know, meeting a lady, hey, what's your flavor? But you're just asking her name, and then she slaps you because that sounds creepy. So they have the same charge, but a much bigger mass. Right, so charmed quark and strange quarks, and then we have top quarks and bottom quarks with a much, much bigger mass. So these will decay into this, and these will decay into this, and these make up normal matter. This make up those weird matter that we haven't really heard of before, leptons, pions, things like that. Okay, so evidence for quarks came in 1967 when a scientist named Friedman used powerful linear accelerator at Stanford to shoot electrons at protons. The electrons scattered much like alpha particles for Rutherford's experiment, right? So you shoot it at a proton, you think that some would go straight back, some would go straight through, but what they actually found is that there's these 3 dense center parts that they deflected off more than other parts, which suggested that there was the 3 quarks inside of a proton that made it up, and that's evidence for quarks. So this is information you have on your data booklet. This is what you need to know. Basically, not even this. Basically this. The questions are so easy. We just like dip our toe into this quark stuff with this last lesson. So don't be freaked out. I'll show you what the questions are like. So what makes up a proton? Well, proton is normal matter. So you have normal matter and you have antimatter. So proton is our normal one, and we know that it has a charge of +1. So if we go back here, we got to be made up of 3 quarks. Well, what 3 quarks? And we don't want antimatter. We just want normal matter. So we have up quark and down quark. What combination could give us a charge of +1, right? If I had 2 of these ups and a down, that would give me +1. So if I had 2 ups and a down, right, that would be, so my up is positive 2/3. Positive 2/3, and then negative 1/3, right? With adding fractions, the 3 stays on the bottom, and we just add up the top. So 2 plus 2 is 4, minus 1 is 3. So positive 3/3 is equal to +1. So a quark, the quarks that make up a proton is up, up, down. Okay, what would make out a neutron? So a neutron is normal matter. So again, we want to just use up and down. It has a charge of 0. So if I had 2 downs and an up, yeah, that would make sense because this would be -2/3 plus 2/3. So it looks like it's 2 downs and an up. So it's made up of a down, down, up. So that would be -1/3 plus -1/3 plus positive 2/3. Again, the 3 stays on the bottom. -1, -1 is -2. That equals 0. It gives me a charge of 0. So a neutron is a down, down, up. Okay, let's do another example. A neutron decays into a proton and an electron. Write the decay reaction using nucleons, and we're also going to write it using quarks. So we have a neutron, which has a mass of 1 and a charge of 0, decays into a proton, mass of 1, charge of 1, and an electron, which has a mass of 0 and a charge of -1, right? Everything works out. But because this is beta negative, we'd have to know that, ooh, this also creates a neutrino as well. So this would be the proper nucleon way of writing this out. Okay. And if we want to write it in terms of quarks, well, a neutron, well, we just said a neutron is made of a down, down, up. So this is a down, down, up, turning into a proton, which we said is an up, up, down. These are not composed of quarks. This is not composed of a quark, so it's a down, down, up, turning into an up, up, down. right? Sounds like a game I play with my son. Teddy, I want the up, up, down, up, up, down. Antimatter. So whenever you're making antimatter, you have to use antiquarks. So identify the 3 quarks that make up an antiproton. Okay, well, let's go back to this, right? And now we want to use antimatter. So an antiproton, well, a proton has a charge of +1. So an antiproton is going to have a charge of -1. So how would we get a charge of -1? Well, we'd use 2 anti-ups and an anti-down. So we'd use 2 anti-ups and an anti-down. Right? Anti-up is -2/3, and then -2/3, and then +1/3. Right? The 3 stays on the bottom. So we have -2, -4, and then -3, and this would give us a charge of -1. So that's what an antiproton would be made up of. Okay, these are your questions. Give them a go. If you have any questions, let me know. So let's finish up with some sample diploma board questions. So to study subatomic nature, high energy particles are required because that strong nuclear force. It's got to overcome that strong nuclear force. D is the correct answer. A neutron and a proton can be modeled using quark combinations. Which of the following rows matches the quark combination to the nucleon? So neutron is 0. It doesn't contain that anti-stuff. Proton is +1. So you have to look up your combination that's going to be 0. So down, down, up is going to give us 0, which makes A the correct answer. Okay, the direction of the magnetic field deflecting force that acts on the positively charged deuterium ion as it enters the magnetic field. So what you need to do is you need to use your right hand because deuterium is positive. So point your thumb to the right. You can see that our magnetic field is directed out of the page, so put your fingers towards your face, and your palm should be facing down towards the bottom of the page. So you end up getting D. D is the correct answer. This one I used to have on a test, and everyone got it wrong, so I thought it's better to do it on a sample diploma question. So make sure you try this before you watch me go through it. So if all the particles enter the bubble chamber with identical velocities, the 4 statements that are supported by the possible paths are. Okay, so you can see that S, T, and U all deflect the same way, and W deflects an opposite way. So that's pretty obvious. It's a charge. And then we have path V, which goes straight across. Well, what's going to go straight across? Maybe a neutrino or a neutron, right? Something that's neutral won't be deflected by a magnetic field. Okay, so let's take a look at this. So particle S and W have the same mass. Particle S and W have the same charge to mass ratio. Okay, well, let's take a look at that. So Fc equals mv squared over r, and Fm equals qvp. Right? And if we're talking about the radius, let's isolate our radius. Let's move that up top, and let's move qb down below. And we'll write it out nice. So mv over qb equals r. So it said that they're all going the same velocities. So I'm going to get rid of this. And they all have the same magnetic field. So I'm going to get rid of this, right? But say I had a mass of, I don't know, 4. And I had a charge of 2, right? Well, what's my radius going to be? Well, it's going to be 2. Okay. Well, what if I had a mass of 8? And a charge of 4. What's my radius going to be? Well, it's going to be 2, right? So saying that they have the same mass, well, that's not true, right? They could have double the mass and double the charge and still have the same radius. So this is not correct, and that's what most people pick. A better way of saying it is they have the same charge to mass ratio, right? Because if this was this is a mass to charge ratio, this would have a mass to charge ratio of 2, this would have a mass to charge ratio of 2. So this is correct. Okay. S and W are opposite charges, yes. T and U have the same charge, yeah. T and U have the same charge to mass ratio, no. T and U have the same mass, no. We can't really say anything has the same mass because we don't know the charge. And particles on V could be neutrons for sure. So it looks like 2, 3, 4, and 7 are the ones that work. And that's all.